Hello class, so this is lecture 2 on water and buffers. And from the last lecture, you know that we talked about water being the solvent of life, so we're focusing more on this topic. And so water have different properties highlighted here. One is cohesion with the hydrogen bond holding the water molecules together. It has high specific heat, high heat of evaporation. So it takes a lot of energy to break those hydrogen bonds for having the water to evaporate. You have low density of ice and then solubilities with other polar compounds. And so the structure of water is depicted here, where you have the ball and stick model, where you see oxygen right here, you see hydrogen right here that is partially positive, and then you have the stick that is representing a covalent bond, and then you have lone pairs of electrons that is partially negative. And so when you see these dashes indicate the actual hydrogen bond. So solid line, covalent bond, or the solid stick. And we see dashes like that. This is representing a hydrogen bond when you see at one end a hydrogen and the other end more of an electronegative atom. And so there are different bonds that are out there. This is just a reminder of the different type of bonds and its strengths. So the strongest is a covalent bond, which is the sharing of electrons. Ionic bonds, which is the attraction of opposite charges. Hydrogen bond, which we just talked about, is the sharing of the hydrogen atom. Hydrophobic interactions where you have hydrophobic portions of molecules coming together due to presence of outside polar substances that does not interact well with hydrophobic compounds. So this is more so hydrophilic substances that is around. And then you have van der Waals attractions. And so when you see the ceiling, let's say a lizard, it kind of wonder like why doesn't it fall down? It actually has a whole bunch of these weak van der Waals attraction that will cause the lizard to actually stay on top of the ceiling. And so we're going to do a little bit of thermodynamics. We will not go super deep in it, but this is just a reminder or introduction of thermodynamics if you didn't have any background. The first two laws of thermodynamics. The first law is energy can never be created nor destroyed. And the second law is the universe tends towards more disorder, so more randomness. So why is all of this important? As the entropy, which is also meaning disorder of the universe increases, creating and maintaining order requires work, and that's why that makes us all living, because we are always creating work because there is disorder within the universe, and that requires work and energy. So living organism exists in a dynamic steady state and are never at equilibrium with their surroundings because there's always disorder happening, so there's always work that is going on. And so we can quantify all of these type of aspects, looking at the total energy, which is equal to the usable energy, which is free energy, and then you have unusable energy, which is the entropy, and that is what is considered the disorder. And so a lot of times when we do the Gibbs free energy, it's in this equation where you have enthalpy minus T for temperature, your absolute temperature, and then entropy, which is your disorder. And a lot of times you'll see the change of your Gibbs free energy in this type of equation where it ends up equaling to the change in your enthalpy minus your absolute temperature times the change in entropy. So these things are very important. And so as far as your free Gibbs energy, in order for things to be spontaneous, this factor, the Gibbs free energy, needs to be negative. And so to drive things to be negative, you have this negative component. So if you have more and more disorder, which goes within the second law of thermodynamics, that makes things a little bit more spontaneous for this reaction. And so, speaking of terms of total energy with enthalpy, and so that is, once again, enthalpy is your total energy. So when you have a product, if bonds are being broken to make that product, then that means energy has to be added in. And so that's why they have H is more, that enthalpy is more. But when you have for the substrate, which is more so of your starting material, if bonds are to be broken, but not broken yet, that has a lower state, and so that has less energy. And so if you're going from bonds that are about to be broken to bonds that are broken, that means overall that you have a energy is being added, and so therefore you have an added a positive value of enthalpy. And so in order to have a positive enthalpy, you have your product, which has a higher enthalpy, minus your reactant, which has less enthalpy, to have an overall added energy to whatever sort of reaction that is happening. So as this relates to water, when you have ice and going into water, you know ice, you have to add heat to have it to melt to be water. And so that is an actual positive change in enthalpy because heat was added. And so once also just to note, the ice, when it's in this crystalline form, you have more bonds, and as those bonds are being broken up and the water molecules are separating, that's where you have less hydrogen bonds that are happening, and that's when you have liquid water. Now, when we're trying to quantify entropy, which is disorder, with that piece, if you have more disorder, S as in entropy is higher. When you have something that has less order, then that means it's more organized, then that entropy is less. And so in order to have in a reaction to have a increasing entropy, so increase in disorder, your product has to have more disorder versus your reactant. And that's how you have the overall positive increase of disorders. Positive entropy, so more disorder. So that goes with ice going into water as well. Well, ice ice has less disorder because you have this crystalline structure, so very, very more organized. And then you have water molecules that's kind of moving around. There's less of those hydrogen bonds to help keep things locked in, and thus there's more disorder. So therefore, there is a positive entropy in this case from ice going into water, and this is a favorable type of conditions because remember, second order of thermodynamics, is the universe tends to more disorder, and water creates that more disorder, and so you have that favorable type of conditions. And remember, as I mentioned before in previous slides, when we looked at that free Gibbs energy, when you just to have it more spontaneous, this needs to be negative. That means this value right here needs to be more and more on more and more bigger to take away from that from the total energy. And so when you have that enthalpy increasing, that term is getting bigger, creating that Gibbs free energy to be more and more negative. And so overall, the magnitude of the Gibbs free energy, which is right here, depends on this equation once again, where you have enthalpy, which is the total energy added, and when it's added, it's positive, or if it's released, it is negative. And then you have entropy, and this depicted the change of entropy. When you have more randomness, more disorder, that entropy is positive. And when you have more order or less organization, that is when the entropy is less. And so positive changes in entropy makes the Gibbs free energy right here more negative, so it's more spontaneous. And then negative changes in entropy makes the Gibbs free energy more positive, which is not as spontaneous. And so talking more about water and this hydrogen bonding, the hydrogen bonding is typically to oxygen and nitrogen, at least for this class. There could be other outside examples, but for this course, we're going to just keep it simple, and you just have the hydrogen bonding towards oxygen and nitrogen. And another note is this hydrogen bond has some directionality, where if you see it's straight up and down, this is a very strong hydrogen interaction. But if you see it at an angle, then this is a weaker hydrogen bond when you see it and depicted in a picture. And so water acting as a solvent, this is what is actually happening. So you have this crystal that is made of salt, and you have sodium, and you have chloride. When they start to disperse, the water molecule is separating the ions, and that is how it is acting as a solvent. And so it breaks it up so much where that's why we see when we see salt and we dissolve it in water and we see it disappear, all it is these ions are dispersing more and more and more where it's not visible to our eyes. And all of this can be quantified. Again, so us thinking as chemists, we want to try our best to quantify things as much as possible. And so the strength of this ionic interaction in a solution of water depends on the magnitude of the charges, which is depicted as Q, and then the distance of the charges, the charge groups is depicted in R, quantified in R, and then the dielectric constant, which is a dimensionless number of the solvent in which the interaction is occurring, is this epsilon, and then F is that the strength or the force of this ionic interaction. And so water has movement. So you can think of water as an introvert. It doesn't like to be around a whole bunch of water molecules. So if it sees space where there is area where there is no water or little to no water, then it wants to go into that direction. So water molecules tend to move from a region of higher water concentration to one of lower water concentration. And this goes within the second order of thermodynamics, where there's a tendency in nature for a system to become more disordered. So where that water moved to, in that area, it was perfectly organized. It didn't have any water or very little water amount. And now that water is going to disrupt that orderness, organization within that system. And so you can quantify this by looking at the osmotic pressure. And so osmotic is this movement. You can think of it as movement of water. And so if you have a tube and you have a semi-permeable membrane for water to go in, you have a solution that doesn't have that much water in it. If you put it in a solution, in a beaker full of pure water, that water will want to go through that membrane because, once again, it's like an introvert. It doesn't want to be around all of this water molecules, so it wants to go where there's less water molecules around. And so it goes into this tube, and if you apply a piston in the tube, then now you can measure that resistance of water movement, and it can quantify this water movement. And so with this equation of osmotic pressure, you have R right here. That is the gas constant. T is the absolute temperature. Then I is the Van 't Hoff factor. And then C is the solute's molar concentration. And so with this movement of water across the plasma membrane, so you have a cell. If it's in the isotonic state, that means water is moving into the cell and out of the cell very evenly. But if you have more salt molecules that's outside of the cell, and so that means there's less water molecules outside of the cell, that means the water molecules that's in the cell wants to come out more, and you're at a hypertonic type of state where the cell actually shrinks. But if you don't have as much water molecules inside the cell, and you have more salt within there, then on the outside there's too much water around, and so it wants to go inside the cell where there is less water, and then you have this hypotonic state where there is cell swelling where the cell might burst. And so if you're trying to remember the difference between hypertonic and hypotonic and trying to memorize it, think of a hippo. So hippo is bigger, so that means that is the swelling if you're trying to remember the difference between the two. And so here is a practice problem where we're trying to utilize the concept of osmotic pressure and using it in a problem. So suppose the major solutes in intact lysosomes, which is a membrane bound organelle, has a major components to be potassium chloride, which it tells its concentration 0.1 molarity, and then also has sodium chloride, which is 0.03 molarity. Okay, then from there, the other part of the problem states that when isolating lysosomes, what concentration of sucrose that needs to be added is required in the extracting solution at room temperature to prevent swelling and lysis of the lysosome. So this is how we do this calculation. We first start off with the osmotic pressure equation and start plugging in. First, find the osmotic pressure of lysosome by itself. And so its major component is the two salts. So you have potassium chloride and you have sodium chloride. Those are your solutes. And so C stands for concentration. The problem already states that concentration of potassium chloride is 0.1 molarity. And then for potassium chloride, the concentration is 0.03 molarity. I stands for the Van Hoff factor. And so that's how things are ionized. So we have potassium and you have chloride. Those two are can be two different ions. And so that is why the value is 2. And then from there, you do your math. And then right now, we have, this is as far as we can go because we have the gas constant, we have the temperature, and now we just did this math of having this new molarity of 0.26. Now we need to find the osmotic pressure for sucrose. And so all we do know is with the osmotic pressure equation, we don't know the concentration of sucrose, which is what we're trying to find. And then the sucrose is sugar. It doesn't ionize. So I is just going to be 1. And then once again, as far as the gas constant and the temperature, that is going to be exactly the same. So that's why that's not defined right now. And so it states in the equation, in the problem, we want to prevent swelling and lysis. So therefore, we have to have the same osmotic pressure of sucrose and lysosome. And so we already found out that for the osmotic pressure for sucrose is the concentration of the sucrose, which is not defined yet. And we have R and T. I is not there anymore because it is 1. It doesn't ionize like that. And then we have what we have on the right side is where we stopped at as far as the calculation of the osmotic pressure of lysosome. Now, RT can cancel out on both sides, and now you're left with the concentration of the sucrose to be 0.26 molarity, and we are done with this problem. And so, as far as buffers, that is the second part of this lecture. It's very brief. What is a buffer's job? A buffer's job is to resist against pH changes. And so buffers are a mix of weak acids and their conjugate base. And so almost every biological process is pH dependent. A small change in the pH produces a large change in the rate of the process. And so the organism's first line of defense against changes in internal pH is provided by buffer systems. So the cytoplasm of most cells contain high concentrations of proteins, and these proteins contain many amino acids with functional groups that are weak acids or weak bases. And so we have an example right here where we have the ionization of histidine, which is a amino acid. And so if something that's more basic between pH 5 and pH 7. pH 7 is more basic, but when you have this amino acid, it is donating more hydrogens to try to decrease the pH. And so that's how it's acting as a buffer. But if it's in more of an acidic environment, it can be protonated, and thus trying to take up more of the hydrogens that's in the solution to help maintain the pH. So that is how that is working. We will go more and more in the details of that later on within the semester. And so, of course, we got to quantify everything. And so this is the equation that is used to help quantify how much of the proton acceptors versus proton donors of this buffer solution to have this overall pH. And so pH is equal to the pKa of the buffer system, and then you take the log of the concentration of the proton acceptor over the concentration of the proton donor. So we'll have more and more practice with this later on in the semester, and your first lab that we're going to do, which involves buffer systems, we will run through doing these sorts of calculations. And that concludes lecture 2.